So good morning to all our listeners. This is Marilyn from PKF's Bitcoin Sessions, and I'm joined today by Dr. Vince from Computime. Good morning, Vince.
Good morning.
Thank you very much for being with us again. And we are live in our boardroom for the second part that we promised, which is the follow-up on last time's session with Computime, which was extremely interesting, and we were very impressed at the very high level of their product and service, essentially, which brings together two of the very most interesting topics of our time, being transaction monitoring and machine learning, and how they brought the two together in a beautiful and tangible dynamic. So what we'll be doing today, essentially in two parts, will be the first block, kind of a recap of what we covered last time, and reminding a little bit what goes into the layering of transaction monitoring. And then the second part, where Vince will focus a little bit more on machine learning proper, and even show us a little bit on screen, so we invite you to follow also the presentation that we'll be sharing live with you in terms of machine learning in application and practice. Vince, on to you.
Good. So, starting a bit at a high level, sort of from where maybe we stopped last time. So, at a high level, we discussed last time as well, we're looking at three main components of this compliant data solution. So we have, let's say, a first component, which is practically the integration of external sources, data sources. So in our case, these data sources would be the operation systems from where basically we're extracting the live streams of transactions, watch lists, KYC platforms, and even web scraping. So scraping the internet for information about particular people, documents related to those people or entities, etc., etc. Then we have, let's say, another key component, which is the machine learning and even statistical data generated on the data that we have collected. And then we have finally the intelligent tools, which make use of the two other components as well. So that is, at a high level, let's say, the three key components of the system. Then we looked at this layering kind of structure. So basically we said that each layer can be sort of imagined as a filter. So we have over here a number of, let's say, layers, each layer acting as a filter on the layer below it. And finally, each layer, so starting from the watch list, you have the rules, you have the machine learning models, you have the intelligent rules, and even we mentioned the importance of the AML users themselves of the application. So you can imagine this as basically each layer on its own is like, it's like a voting mechanism. So when I have a transaction, each layer will tell me, like, in my opinion, this transaction is suspicious, or in my opinion, this transaction is not suspicious. And like the whole mechanism can be seen as sort of, have these kind of independent, let's say, advisors, let's say. Obviously, the AML users is a human advisor, but the others are, let's say, software or intelligent advisors. And then the way it works, that is, everyone is giving his opinion, let's say a voting, and then based on the sort of, the voting of the individuals who are taking a decision. So if, for example, the intelligent rule is telling me that, and the watch list is telling me that that person is this and this, so okay, then the, let's say, aggregate kind of outcome should be what? So this is important. So we're not basing kind of our, let's say, final decision on one, let's say, layer, but obviously on the aggregate kind of feedback that we're getting from each of these logistics, one of these layers.
Is it always unanimous, or is it sometimes the different sources point a little bit not unanimously?
In a sense, unanimous. I mean, it's not, I think, a question of keeping stuff unanimous here. I think it's more a question of, because, for example, an AML user might have certain knowledge that maybe no algorithm kind of would have captured that particular, for example, suspicious transaction. Or, on the other hand, you might have a machine learning model which captured something where the AML user would have thought that that transaction is not suspicious, for example. So I think it's important, like instead of having one person, let's say, just monitoring, let's say, the transactions, you have, let's say, a pool of people, and then you're getting the opinion, let's say, of 5 people. So obviously that makes, the system more robust,
yes.
right? So the two top boxes are as well something we mentioned last time. So the live environment and backtesting environment is a very important concept as well, which is very common in a way in a machine learning kind of in the machine learning world, let's say, that you never have, let's say, just a live environment, but it's very important to have as well a backtesting environment. Why? Let's take something in practice now. So the difficulty, let's say, especially, let's take fixed rules. So for example, I have a rule which is saying when a person is coming from that country, is depositing a value greater than this threshold, whether it's a PEP or not, then that transaction might be suspicious, for example. And, you know, it is something very clear. And you decide, let's say, okay, maybe I should change the threshold. The biggest difficulty right now, if you don't have the backtesting environment, would be, okay, what if I had to lower that threshold? What would happen? Will my number of suspicious transactions fire? I don't know. Instead of having 1%, I will get 20% of the transactions suddenly being marked as suspicious. So it's very important to have, let's say, an environment where you can calibrate your rules comfortably, and sort of, you know, by doing these changes and turning knobs, let's say, you are seeing the effect on past transactions. So if I had to look back, for example, and use my last year's transactions on the backtesting environment, what would happen if I had to fine-tune these rules? And this is an extremely important, I think, in practice requirement, because sometimes you find, for example, users who maybe, you know, they are maybe afraid, or sort of they would think twice before, let's say, changing a rule, because they have no clear idea of what would be the effect of the change, right? And don't forget that at the back here, I mean, we're thinking, I mean, you have to be very careful, because sort of, you know, there is always this balance between being too stringent, which is not good, because obviously you can scare away your clients. But on the other hand, you, as much as possible, obviously you have to abide by the AML regulations and obviously raise suspicious stuff. So it's a very fine line. So this backtesting environment is sort of an extremely important kind of requirement.
Very much highly mathematical from the sound of it. It has to be very thought out. Is it correct? I'm getting the image of what you do with this backtesting, like a magnetic board, and what you do pins on it, and then when you change the knobs, you get a different graph.
Exactly, I mean, it's pretty much, exactly, you need this kind of, pretty much like that. So you need to, it's like tuning an engine, really. So you have a lot of knobs, but you need kind of this facility that, okay, if I turn a bit this knob, what is going to happen? And funny enough, we find a lot of systems where they perform well, kind of, but sort of they do not employ this kind of backtesting kind of thinking, where I need to not just be able to set rules and sort of intelligent stuff to monitor transactions, but I need as well a facility to sort of be able to fine-tune it and be able to test it before pushing it live. Otherwise, you'll have sort of the AML guys will be very kind of, you know, won't be comfortable when they want to test some sort of, you know, changes, etc. Because one will be worried. Okay, you know what is going to happen? Will I have my VIP suddenly be marked as suspicious, kind of thing, and sort of, so it's and scare him away, kind of. So it's a very important requirement, this backtesting.
Is it not a market standard to have this back?
I don't think, I mean, it sounds something obvious, but in many cases we found out that although maybe it sounds obvious, it's not always the case, right? So we find a lot of situations where backtesting environment is not. Yeah. I mean, in a way, from a machine learning perspective, funny enough, this is pretty much common, in the sense it's a standard way how you build models, right? When you're modeling and building models. So it's pretty much, so you need sort of, you know, to look at past data. And so if I had to do it sort of, you know, for example, I move in a company, we start implementing the system. We know, for example, last year, for example, we have your own history. So we know that, for example, from, I don't know, 100,000 transactions, you had those particular 400 or 500 which were really suspicious transactions, etc. So by running these new models, the question would be, would we have picked up those 500 transactions? Would we have picked up more? Would we, I don't know, would we have reduced the false positives? So you need this kind of backtesting.
Definitely. And do you actually go in the backtesting and this analysis of retrospective data into those that had been flagged as suspicious? What happened So what I mean to say is
Exactly.
if it's actually resulted, say,
Exactly.
in an investigation.
Because obviously suspicion is the first step, but then obviously a lot of suspicious could be a lot of false positives as well. So it's very important to sort of, this is the tuning, sort of that, let's say if I had last year, if I had 5,000 suspicious transactions, and then it resulted that only 100 were really kind of possibly, potentially fraudulent, let's say. Then with our system, we need to test whether from those 5,000, whatever, we reduce that figure and actually manage to pinpoint as much as possible those 100, right? And that is the tuning and calibration which needs to happen.
But if I may, so this is a bit of a delicate question. What would be the benchmark to make a client bet? So if you find 500 potentially suspicious, potentially fraudulent transactions, what would be the marker to hold on the reins and say, this is can't go on, for example? Is it the first one that translates into an investigation, or is it a series of red flags that have been picked up?
Let's face it, I mean, from a practical perspective, worst case scenario, extreme case, let's say in an extreme case, you have a person who is, let's say, monitoring manually each transaction, meaning that you're investing a salary every month to monitor every transaction, if that is anyways possible. Obviously, I have thousands, 10,000, you would need probably hundreds of people to do it, let's say. And then you have the results. So those people managed to raise X amount of suspicious transactions, out of which Y% were really kind of something that need to be followed up. So we start from a benchmark in the sense, okay, what's the current state? I don't think that normally people would obviously monitor everything manually and sort of spend kind of, whole things monitoring every transaction. So typically they will base things like, they will be using sampling, rules where sort of things maybe that are obvious or breaking sounds that obviously they will pick up those. So typically, because every client typically has his own story, right? And not everyone is the same. So it's very difficult to pick up a benchmark and use it throughout. Why? Because every client would have specific transactions, would have specific products, would allow certain transactions, other would not allow them. So it really depends on a lot of combinations. So I think what we do typically, we say, okay, this is the current state. We look at the amount of investment that is being sort of, put it at this point in time to be able to monitor. We look at results, meaning sort of, okay, how many false positives, for example, are being generated, because obviously that means a lot of inefficiency in the process. And our target typically would be obviously to start showing how much we can improve on that process, how much more efficient we can make it. Even if we improve by X%, I mean, for us, it's only, let's not forget as well that it's very difficult, like even from a modeling perspective, it's very difficult that you, from step one in your life to the ultimate in one stage. It's always, this calibration thing is always, it's a journey, right? So we start from there, then we say, okay, let's start improving. That means we're becoming this much more efficient, meaning that investment, okay, we invest in the system, but like our expenses in this case can reduce by this much, etc., etc. So these are the benefits. I think that this is how we reason things out, and this is the whole journey that we go through.
That makes sense. So you're finding mathematical or is a very complicated way of calibrating is made further.
Let's say you have to follow, let's say, a scientific approach. This is the current expenses, this is the current effort we've been doing. Okay, putting it in the system, these are the improvements in the results, these are the efficiencies that we target to gain. Let's say. So we started mentioning the components. So we mentioned the fixed rules. These are sort of, important. So because they are one of the layers, so the rules are, let's say, if then conditions. So very simple to think sort of about these rules. So let's say, for example, if I have a deposit greater than a certain threshold, then I put a flag. Or if, for example, combinations, if there is this deposit coming in from a particular country, or in addition, that person is a PEP, for example, that is a suspicious transaction. You can group as well, like, for example, if the total amount of transactions over the last few days was greater than a certain amount, or frequency, if X amount of deposits happened in the last 2 hours. So it's a frequency based, how many deposits you've done over a period, for example, or withdrawals. It could be a velocity thing. So I've done a deposit or withdrawal, a deposit, let's say, and a withdrawal of a similar amount was done in less than 15 minutes, for example.
And these are also tailored to which clients or can they be standardized?
Normally, the way we work is sort of now with experience and even companies that we collaborate with, and even sort of lawyers, etc. Because I'm not a lawyer myself, so I'm not the best guy maybe to transpose the laws to something sort of to a system. So I need probably assistance to do that translation for us. So normally what we do over time, we have definitely now a set of, let's say, standard rules. So when we start an implementation, we typically have a number of rules where sort of the system comes with these rules out of the box, let's say. However, then it is always the case that that is really a starting point, and then those rules are tuned to the specific business, as I said. Since every client would have his own story, his own products, his own services, his own policies. So typically, they are a good start, definitely, but then there is always this fine-tuning that needs to happen as part of the implementation.
So these rules are thrown up by developers into code logic.
Exactly. Let's say these are, a collaboration between, experts in the ML field, technical people, brought together and obviously trying to translate the law into rules. Let's say, right? And these rules as well, the complication then starts to start this level one notch up, is as well sort of taking consideration, for example, relationships. So it's not like, for example, just a threshold based on an individual. Let's say if it's a bank, for example, the threshold, for example, of the total deposits could not just be on an account, but at a client level. So combining all the accounts of that particular client. Or it could be that a threshold or a condition is based as well on relationships, we call them. Not so, let's say, a threshold which is, for example, exceeded, and that amount that we're comparing is based on the accounts of that particular person, for example, his wife, for example, or any relatives, or his company. So it's not just his own personal accounts, but in relation as well with his company accounts, right? Or involvements in this company, like between directors of the company. So these rules, this is where they start to sort of, to get a bit more complicated.
You keep like a book, not an actual book, but you keep a place where you have this beautiful compilation of all these rules, and maybe as they change over time, like a detailed record of how they've been modified and why.
Yes, definitely. I think it's part of the system as well. It's very important because you need to keep an audit trail of kind of these rules. Let's say, because these rules is like, each rule is like a key kind of to allow my transaction to pass through, right? So if someone, let's say, maliciously can go in and let's say lower a threshold kind of in the sense, or sort of makes it easier for the transaction to pass kind of thing. No, I mean, even internally you have to get control. So even as an internal practice, it's very important that if a rule is changed, we keep note of when it changed, we changed it, etc., because sort of, it's very important to keep note of these things. We mentioned as well there are sort of blocking rules and non-blocking rules. So in this sense, for example, you might decide that you have situations where, for example, a bank would take a stand as a policy in they will not, for example, accept transactions coming from that particular sanctioned country.
Okay.
So in that case, the transaction is blocked before even hitting the operation system. So it doesn't even flow into, let's say, the internal systems. It's blocked immediately. It's like, in a way, it's like a firewall kind of mechanism, which sort of at the transaction level, which blocks transaction before even hitting the system. And there are those, let's say, non-blocking rules, which means that transactions are still allowed to flow into the systems, a banking system or a gaming platform. We are still notified, so the transaction, the AML guys are sort of notified about this transaction, and then in parallel there is this sort of process which is happening kind of on the side where people are getting involved. You have the machine learning algorithms to start pushing their suggestions, etc. And let's say a decision is being kind of taken or being analyzed in parallel, right? So you have different situations. There are the obvious rules where you would say, let's say, no, definitely I would not like these transactions to flow in, and there are others which obviously would need investigation.
Okay.
Right? Then we mentioned intelligent rules as well. The intelligent rules are rules, let's say, which are combining those layers that I mentioned together. So this is, let's say, sitting on top of those advisors, let's say, and the rules would say, okay, then if my machine learning algorithm is telling me this, and sort of, my rule is telling me this, and this guy, that kind of, when I checked against that backlist, it's telling me that this guy is a pap, then sort of I want to take this decision. It is, let's say, this layer which sits or combines the voting mechanism kind of over these kind of individual, let's say, advisors, let's say. So these would be the intelligent rules.
The machine decides.
It's actually, the machine learning is just one voter, let's say. We consider it that way. Really, you have like the rules, but then the machine learning, which is another layer, it's again another voter. So it's like it has a voting kind of ability, let's say. And then it's up to you how much weight. It's like, imagine we're a group of 5 people here, and either I'm completely democratic, so each one of you would have an equal vote, let's say, or else I can as well have a situation where I'm putting more weight, let's say, on the say of a particular layer, right? And this typically is part of the learning mechanism from the machine learning perspective. So you are actually giving weight to those layers which are normally giving me the best results, right? So imagine if you're in a class and I ask a question, I could be totally democratic and ask for an opinion, let's say, and sort of I'm equally valuing all the opinions. However, I can have a situation where if with time I know that student A and B are typically the high flyers, let's say, and they give me an opinion, their opinion I give more weight. It's exactly the same thing, right? So this thing, it can actually sort of, it's not really something that's rocket science, although it might be, but it's not really that. It's really on the model, on specific inputs, I'm attaching more weight, right? And it's really mimicking this sort of setup that I'm telling you.
So ultimately, the person, human, decides which student's opinion to give more validation.
Actually, the human can be part of this formula, right? So I can decide if I want that the decision of the human, I'm giving it the full weight. Right? Right? Or otherwise. So it's up to you how to calibrate kind of the model, right?
Okay.
You could have a situation where you could have, let's say, because it's really pretty much this environment, you could have one player, let's say one let's say layer, this kind of one advisor, let's say, that has, let's say, the veto power. So whatever he says, I have to sort of, just take his advice. Right? So, and it's up to you how much weight you put on each one of these advisors, whether the intelligent ones or the rules or the individual.
And this plays into your backtesting.
Exactly. This is all the calibration. How much weight I'm going to give to the machine learning, how much weight I'm going to give to the rules, how much weight exactly. And by changing the weights, you're actually going to affect the results, meaning how many false positives I managed to reduce, etc. So this is how it works.
Very, very interesting.
So I mentioned the AML users approval. So we said it's very important that there are obviously humans involved to take final decisions, especially on, let's say, those transactions which obviously could have some repercussions as well on the business. So, for example, in the sense, for example, if you have, let's say, you're monitoring VIPs, you have to be obviously very careful. One has to appreciate, obviously, that with VIPs, yes, obviously there is the possibility of illicit activity, and obviously we all have to be careful from that end. However, obviously want to make sure not to lose kind of any of the VIPs, for example. So, user approvals kind of are very important in these certain instances, because it's a very important decision, and it's a very fine line, right? But then there are situations where AML user approvals are not really required, because if, let's say, as I mentioned, I have a strict policy that I do not, for example, accept any transactions from the specific country, for example, then really and truly I don't need an AML user to get involved, because that's a standard policy, pretty much, this sort of, it's a fixed thing that I don't need any approval for that, right?
Question: what qualifies a person as a VIP to you? Say to us, it's typically someone who, affords to buy passport by investments in our game. But to you, is it just the wealth, or is it a combination of factors?
No, I mean, VIP, I'm maybe using it sort of, taking, let's say the jargon from the game or whatever, sort of this kind of it. But honestly, the VIP could be anyone, right?
Okay.
It really, in the sense, it really depends on each company and how they define a VIP for them. It could be based on that, but for me, it could be a VIP someone from a particular company that I know about, and sort of, strategy is very important for us that we give them an excellent service, for example. So slowing down the process of that particular company, let's say, would damage our business. Let's say, so VIP is really good, you can define it.
Okay.
So, and we mentioned the dashboard. So the idea live now, because Comply Radar, in our case, we try to, as much as possible, focus on this live importance of having a live system, so not sort of using this kind of maybe more traditional approach where, let's say, regularly, so whether it's daily, weekly, monthly, I don't know, but let's say on a regular basis, using a system which is more sort of more the likes of a reporting system or a business intelligence solution where you're issuing reports. That means that it's based on sort of past data.
Right.
But over here we're looking at live systems. We believe the advantage of this is that in many cases, if a suspicious transaction happened a week ago, for example, it might already be too late, right? So the quicker you can detect these kind of suspicious transactions, the more efficient and the more likely that sort of you're in time, let's say, to act on it. And sort of reach an outcome kind of it, right?
How do you manage to do the live part? Is it a matter of attaching your system to many live stream sources?
Yes, so in many cases, sort of transactions, so this is where, so when it comes, we're deploying the solution, we are sort of, we're obviously speaking with the guys on the other side, and obviously from a technical perspective, it starts to get a bit more complicated technically, let's say, in the sense, for example, let's take one of the implementations where you're monitoring, for example, 800, 900, 1,000 transactions a second, right? So technically it starts to become a bit of a challenge to be able to monitor all those volumes. So we're speaking about huge millions of transactions a day. From a technical perspective, that would be one of the biggest challenges, to have a system which can cope with those volumes, right? Because it's not just injecting them, but obviously we're monitoring. So we're sort of, we have our rules filing account being sort of checked against each transaction. Our machine learning sort of needs to look at all those transactions and label them. So there is a lot happening. So yes, the challenge technically would be to be able to handle those volumes. So you can't just apply, let's say, any technology. You need technologies which are, let's say, more adapt to these live kind of huge volumes of transactions. It's more data streams rather than just looking at past transactions, kind of, right? So I mentioned the backtesting. I think we mentioned this. Don't need to sort of maybe delve there now under the hood as well. So maybe some more sort of for more technical terms now, the tools and technologies that we're using.
Yes.
So we have the rules engine. So now these are more, let's say, getting into technical terms and jargon, what components we're using. So we have the rule engine, which is sort of the transaction monitoring, the processing. We have the segmentation, so automatically transactions coming in are being segmented and this is dependent on the client. So for example, we mentioned VIP. So automatically when transactions are coming in, automatically they are being labeled and placed in a segment. Let's say this is a VIP transaction.
Okay.
But you could have multiple segments and overlapping segments. So VIP, but coming from, and it's being as well segmented as a non-EU, for example, transaction, or being segmented as a big part of a set, which is, for example, the under 25-year-olds, for example.
Okay.
So you can create as many segments as you want. And then based on those segments, you can as well then apply the rules, because the rule can be segment-based. So I would have a rule for transactions which fall into the segment non-EU, for example, transactions, and I would have a rule which is specific or based on segments which are EU transactions, for example. We're running, the rule engine is running these profiling and statistics. We have the machine learning as part of this, let's say, block over here, and we have the actions, because it's one thing identifying something, and then once you identify it, you need to define as well what action is going to be taken, right? Could be a block transaction, could be send an SMS to someone, could be send something for approval to a user. So these would be all actions subject to what I sort of whether the transaction was marked as suspicious or not.
Sounds like very intricate architecture.
It starts to get quite complex. It's sort of a more sophisticated to go. You have what we call the REST API. It is very important that such systems are open as well to other systems. Let me tell you why. For example, just a simple example. It's very important that, for example, if I have a CRM system where I have sort of, I'm logging in my new clients, I'm sort of putting all the information, what service they've bought, all the activities that they are having with my company, etc., etc. That system, it's very useful typically that gets information as well from our platform. So when I'm looking at the client card, let's say client form, I have as well information coming from our system. What transactions this person has affected, the type of transactions, their size, etc., etc. So it is very important that it's open for other systems, both for other systems to extract information or for other systems to push information to us. So for example, bringing the same example, if someone suddenly goes into a CRM sort of system and goes to a specific client and suddenly marks that client as being a PAP suddenly, that system needs to inform us that sort of from now onwards that client is suddenly a PAP. So we need these systems to communicate with each other, right? So you need this kind of layer to allow these systems to interface together.
So your dance with machines became a more dance.
And finally have the UI. UI is sort of this layer, which is what we mentioned so far, is sort of pretty much hidden to the business user, let's say.
Okay.
So the UI is that layer which hopefully sort of tries to hide as much as possible the complexity is running behind and makes it easy for the user. And today, if we have time, that's the idea at least, we have to go through some screens to give an idea of sort of what this UI looks like for the actual user. Below the boxes in black, I'm showing some of the technologies that sort of, as well, key technologies that we're using underneath, kind of. So we're using Kafka, which is sort of a layer which is sort of can allow this kind of huge influx of, let's say, of data streams coming in. InfluxDB, which is, let's say, a time series database, which allow us to sort of do some complex, let's say, querying on this kind of time series data, because a stream is actually a time series data set. You have a number of points coming in all the time.
The live.
Yes. We have MySQL, which is a database, and we have MuleSoft, which is, let's say, a component which sort of pipelines a lot of the components together, allowing them to speak between each other, let's say. Now we'll start getting into the screens. So let's say there's a typical dashboard. So in the dashboard, for example, when you go in, you have, let's say, at the top, you have, for example, me, and this is live. So sort of when you install it, you see the numbers changing live, right? So I see, for example, the number of transactions coming in. So automatically I have a gauge which is showing the number of transactions coming in, and the number of, we call them flag transactions, right? So those kind of that immediately sort of when then they are already kind of tagged as potentially they need further kind of analysis. And then let's say we have the others, which is, for example, checked. So the flagged are mostly the suspicious one, right? Once they are suspicious, then they become checked. So okay, once they are suspicious, what would be the final outcome where they sort of, it's another layer. Once they are sort of, you get them marked as suspicious, and then move to into a process, and finally the ML user would say, yes, this is something which is really suspicious or not suspicious, right? And finally, I have sort of, the final stage, which is really, because I think we mentioned this last time, we could have situations where the transaction kind of flowed through all the layers. It was not captured as suspicious. Then a month passed or 2 months passed, and you get to know later that that was kind of transaction with illicit funds.
Right.
So it was not captured. So it's very important for us to get as well on the dashboard that information of what we didn't capture, because it's very important, because that will allow the user to know, okay, how efficient is the system. The system needs to learn from its own mistakes, let's say, and it is sort of, and that is how the system can as well improve and make sure that next time kind of it captures the transaction. Then we have this kind of box over here which is saying flagged by level, which can show you or depict kind of the layers that we showed before, what each layer is capturing. So I might say, all right, I have a particular layer which is sort of flagging much more than the others, right? Is it right? Is it wrong? Is it because it's much better, or is it because maybe it needs to be fine-tuned a bit because of it's raising too many suspicious transactions, right? So it gives you a feel of how many suspicious transactions are being raised by each of the levels that we mentioned before. Then in the middle over there we have let's say a line chart kind of showing as well the flow of kind of suspicious transactions in time. And I think it's very important because typically, if let's say over the last month, for example, you have an inflow of suspicious transactions, it's very important then sort of, to know this kind of change in pattern, because, you might say, oh, something is happening. Last month, suddenly, the number of suspicious transactions that peaked, something is happening. And now I'm mentioning a month, but it's been within the day. So if the number of suspicious transactions in a normal day is X amount, typically, I would need to know if there is a particular spike. That allows me to act immediately, something is happening. Then at the bottom you have sort of, you have the top, for example, on one side you have the top 5 rules that were fired, and that gives me very important, because it gives you which rules are sort of, the most important, which are being the most effective.
Okay,
right?
it does that on its own.
Exactly. It's telling you, give me a statistic. If I'm putting, let's say, 20 rules, 50 rules, which are the rules which are, let's say, generating or capturing the most suspicious transactions? Per client in general, as you wish.
Okay.
And that's important information, because it will tell you which ones are the most effective, right? On the other hand, it's giving you as well those which are the least effective, or those that resulted in a lot of false positives, because that will give you as well input on which transaction, on which rules maybe need fine-tuning, right? Because it's very difficult sometimes, because when I speak fine-tuning, it would be quite a complex exercise. Let's speak only about rules. Rules, we wouldn't have just 2 or 3, you could have 20, 50 rules, right? It's very difficult, and let's say those rules are giving you, let's say, I don't know, a huge amount of false positives. Obviously, you need to start from somewhere with the tuning, and with 50 rules, it will be very difficult if you just look at the final outcome to know which rule would we need to tune, right? So by knowing which rules are being the most effective, and the ones which are, let's say, raising, the most suspicious transactions, which were not really suspicious, it gives an idea. So we can start honing in on which rules you need to maybe adjust and tune, right? And the final chart over there, that circle over there, is giving you as well an idea of how many transactions came in, flagged suspicious transactions came in, right? And it's giving an idea of the delay in terms of, let's say, if you didn't take any action on those suspicious transactions. Because there are these stages, there is this kind of the stage where, okay, there is the transaction coming in, then it's flagged as suspicious. And then, for example, an AML user needs to act on it and decide on what's going to happen. So we're trying to give the information to the user that, for example, if there was a transaction marked as suspicious and no one acted on that transaction for the last 2 days, then it's telling you, that falls under the red part, for example, because sort of there are a number of flag transactions which I didn't decide on what I'm going to do with those transactions.
And by the unexpected, that's what
Exactly. That can be fine with us, but it could be a policy where I say, as an account, I need sort of to act on suspicious transactions, on a suspicious transaction maximum within a week, or within a day, or within an hour, depends. But it gives you an idea of how much sort of backlog, let's say, you have.
It's entirely at the discretion of the user.
Exactly.
Interesting, because it reminds me of the work, the FIU in a way, and all that we hear, the logic to the timelines in which you must report when they do decide it is suspicious and whatever. But then actually before that, it is all very relative. Everybody has a free hand to set his own risk appetite policy as to when to blow the whistle on actually taking it further or not.
Yes.
So it is very fluid.
Yes. And you need at least an idea of how sort of, how of your backlog. I mean, it depends, because it really helps as well the team to manage their load, right? Then there's another screenshot. So, for example, in this screen, I went into a particular customer. Let's say I'm looking at the particular suspicious transaction. I can open the transaction. I know the date. I know that it's a withdrawal, for example. I know the rules which fired kind of against that particular suspicion, that particular transaction, so I know why it's marked as suspicious. In this, exactly. So I know, for example, that this particular withdrawal, it went beyond the particular withdrawal risk score threshold, and even the rule, it fired against the rule, the instant withdrawal alert. So, because we have a rule that, for example, if you do a withdrawal of a similar amount and that you have deposited in the last 15 minutes, that fires as well that rule, kind of. So this kind of transaction, for example, was, let's say, alerted by 2 rules. So we would not blocked at this point. Exactly. Not in this case, for example, it's set up that the AML sort of user is alerted. He knows which rules fired against this transaction. He got notified, and at this point he can sort of approve, or even this transaction can even move. For example, in this case, in fact, it is escalated. You have that note escalated to manager. Right. So you could have this kind of escalation as well, this kind of workflow. So you might have, let's say, the first line of defense, which is, let's say, sort of handling particular transactions, looking at where or which rule got hit by that particular transaction. And then it could be that for certain instances you have, let's say, a second line of defense, where then that information is passed to a second layer, and then it is that second layer which is taking a final decision, right? So this is kind of sort of showing at least an idea of this screen kind of suspicious transaction or particular customer. For example, they can obviously filter by date, by type, and sort of do all the drilling across all these suspicious transactions being raised. Once you're from here as well, an important thing is that once I see a transaction, I can drill down, because obviously one question you would ask is definitely, okay, what do I know more about this client? Who affected this transaction? And then I move into another screen, and from this screen I would have, for example, a history of all the suspicious transactions I had about this particular client, right? And over there you're seeing segments, so I'm seeing, for example, under which segment this system sort of placed him. So in this case he was under high risk customer, right? I have statistics from his past transactions, and those 2 boxes you see below, that is information that was automatically scraped from the internet. For example, in this case, we have, for example, his LinkedIn profile. So obviously you would know, okay, this guy affected a transaction of $500,000. Let's say, okay, who is this guy? What is his background, right? So we know his background, where he works, etc., etc. We scraped information from Facebook, so from his Facebook account. So we're trying. So first, in the first screen, you've seen sort of the transaction, the actual transaction, which rules were fired, which alerts were raised. Then when we clicked on that customer, we came into here, and this allows you to go to the next level of detail, sort of looking at his past transactions, what happened, and even information about a particular client, sort of from public information in this case. But it doesn't need to be public. Obviously, if you have a paid service, you can as well scrape information from paid services and even have it here available here. So we're trying to build kind of a picture of the individual for the AML user to obviously be able to make, let's say, an educated decision about this particular transaction.
Can we mention some paid services, what they might be?
I mean, there are a number, I mean, to be honest, but I mean, if you look on the internet, like, or even like these kind of PEP list, kind of watch list providers, I mean, these are a lot of kind of, and sort of even companies providing information about his credit situation, kind of, a lot of, it could be even sort of, you know, for example, information from law courts, etc., to see whether this person, for example, had any cases recently at court. So there are a lot of services. Abroad as well, you can even find situations, there are websites where you can put in the details of the particular individual, and it can give you, for example, information about his household, where he lives, with who he lives, how many people live with him, you know, family background. It's sometimes, and what's funny, sometimes it's probably scary, sometimes I mean, people sometimes do not imagine the amount of information you can extract about them from the internet, and a lot of this is actually free. So this scraping sort of, you know, brings as much as possible all this information, because you could tell me, yes, there's at the moment what in practice a lot of MLROs or sort of people in the ML kind of department do, is that when they have this transaction, they would go website by website kind of and try to sort of, you know, get a bit of information on that website and a piece from that website, and they do it as pretty much a, let's say, a sequential process, right? Searches through Google, sort of filtered, some very intelligent kind of Google search kind of mechanism where sort of, you know, they try to, over the years, they built a search string and they try to see the top hits from Google. All this information is typically they scrape it, but they do the process pretty much in sequence, right? What we're trying to do, to facilitate at least, is we're trying to mimic this process, and as much as possible, as a kind of step, kind of over here, we try to bring all this information together in one screen automatically. To be honest, it's not always the case. In fact, we would have cases where, because it's very difficult to filter all the information. Probably if I, for example, in my case, I look for Vella, definitely you'll find about me, but you'll find about other Vellas. So, and the difficulty sometimes is obviously try to filter out other events kind of from the picture. So what we do typically the first time when you're building this customer details, you get as much as possible information, we'll try to filter out as much as possible. But then if you find some irrelevant information, you can actually click on those boxes and remove them. Once you remove them, the next time you go in, automatically that link, the computer will know, it will not bring that link again, because it would already know that you have filtered it way back, right? So we try to do it that way. Let's go.
Highly investigative as well.
Then this gives you an idea of the rules. So this sort of the standard rules. So you have all the rules over there. So for example, you have the deposit risk score threshold, withdrawal risk score threshold. So these are all rules which you can switch on or off. It's very important that you can switch on or off. You might ask me why. You have situations where, for example, let's say gaming companies. We had the World Cup, for example. You might have certain rules which you apply during specific events, for example, or switch them off, right, during specific events.
Because you expect a higher
exactly.
Because it's the World Cup.
Exactly. So you can switch them off. You can even schedule them. So they can kick in, let's say, during specific times or during the day. Okay. For example, we have situations where when, for example, during the night, where obviously you don't have someone physically there, they apply certain rules, so you have that level of extra kind of, you know, watch exactly. But then during the day, automatically those rules are switched off.
Okay.
So once you go on a rule, you get something like this. The screen will actually define the rules. So for example, this is the deposit from high risk country, and this is quite easy. So we have the filter, and it's like, you know, over there defining the conditions. So for a filter, I'm saying if the base amount is greater than, for example, a single deposit threshold, and the country is a high risk country, then that means for me is a suspicious flag transaction, right? And over there at the bottom, I'm as well, in this case, I'm defining the action as an email. So I'm defining the template like of the email and to send it. So if this transaction is flagged or transaction is flagged, then send an email to this person with this information, right? You can as well define variables in the rules. So you can define a measure, because a measure is, okay, what I'm sort of, in this case, for example, is the deposit is the amount, right? Yes. But it could be a calculation. Could be, for example, the measure that I'm using is, for example, taking an average or taking a sum of something. I'm interested in not just a measure, which is sort of just a data point coming in, but I wish to do some calculation of it. So the average number of deposits, you will not, obviously will not get the average number. You, as a flow in this scheme, will get the individual deposits. But as a measure, as a calculation, I want to create a new variable which will automatically calculate for each individual client his average amount of deposits. That will be a calculate exact per week. Exact. You can define as many of these variables as you wish. But then once you define the variables, you can use them in the rules. So if I define, for example, the average weekly deposit, then I can have a rule which says if the average weekly deposit is greater than something, so this is how you define these calculated variables. Or
manifestation of human intelligence.
or statistics, right? So I'm saying like averages, but like things that if, for example, in the law you get, for example, this kind of definition, if it is out of profile, a transaction is out of profile, how would you define something as out of profile, right? So over here, what we do is we have, let's say, a distribution of each statistic, let's say, of each variable that we're getting for each individual. And once we have that distribution down to each client level, then from that distribution we can identify whether it is within his profile or out of profile. Now I'm mentioning an individual, but a distribution can be as well at a segment level. So rather than just on an individual, I could have what's the typical profile of someone working in that role in Malta, for example, right? So I have my statistics as an aggregation, let's say, that my distribution is an aggregation of all the transactions coming from people which fall in that particular segment, right? Or I could have a rule or a statistic which is based on all the people aged between 20 and 25, let's say, right? So these are all statistics which we can build, and then we can apply in the rules. Now move a bit into the machine learning. Some few slides on machine learning. What's important for machine learning? Because, okay, so now what do you need to pass to an algorithm kind of? So the first step is obviously you have to decide what data you need to use or utilize or make available for the machine learning algorithm to make it learn, let's say. So you need, typically, these are some of the data items that would require. So it's first in the reference data, so the list of clients, their accounts, balances, segments that they fall in, etc., etc. We need the transactions, obviously, so amount, currency, the source and destination. So such the source, but typically we need the destination information as well. Very important. We have statistics that we generate, so distribution of the transaction values, the frequency, what we mentioned, frequency, velocity, is all data that we generate typically from the raw data set that we get. We have what I'm calling here time deltas, so the changes. So we generate as well from the raw data, not just take the raw data, but we're interested in changes in the data, so movement. So not just balances, but we pass as well changes in balances. Because to the machine learning algorithm, the change could actually be an indication, not the actual balance, right? So what if, for example, this person typically deposits values between 1,000 2,000 and suddenly deposited 500,000.
Right.
That change could be the indication that something. Relationship data, from a technical perspective, there are these called graph data as well. So to give you an idea, this kind of the ICIJ thing, like where you have, let's say, nodes and edges between those nodes, right? And each node could be a person or a company, and an edge is a relationship between those nodes. And from a machine learning perspective, in fact, it is quite a recent thing. There's quite a lot of research happening where you're not just feeding normal, let's say, tabular data to machine learning algorithms, but we're feeding sort of graphs data, so a whole graph. So meaning we're passing all the relationships, and actually the outcome could be as well a graph. So I would know whether that particular node is suspicious or not. So if I have a node of 5 people linked and 3 of them are suspicious, then basically we're defining the problem. Okay, then this node, which is linked to this and this node, what is the probability that that node is suspicious? So looking, sort of feeding information as a graph rather than just a tabular list of data kind of thing.
The algorithm is essentially a piece of code.
Yes.
How when you give it access to all this data, it's like food. You feed it.
Yes.
And you feed it graphs, you change the food, making it more complex.
Exactly.
How does the algorithm, what effectively makes it learn? Is it still a logic-based point of departure, or is it something different?
I mean, sometimes the people sort of, this maybe a bit of hype at the moment about AI and machine learning, right? Maybe a lot. But at the end of the day, and they try to sort of, or maybe it's explained as we're trying to mimic the human mind, right? But honestly, I don't see it like that, and I think that is part of the hype, maybe. Because at the end of the day, what we're trying to do is fit a mathematical model, right? And there's no brain matter in it. It's really trying to fit a mathematical model, and sort of it's a very kind of what we try to, as much as possible, maybe sort of beautify this idea by saying so we're fitting this model, and basically this model is telling us the outcome. In many cases, it's a binary one, whether it's suspicious or not, right? So we're really trying to get this outcome. Now, by making the food, we mentioned food, by giving more, let's say, food which is, let's say, passing more nutrients, if I have to use this analogy, let's say, it's like, if I'm going for, I don't know, if I'm going to the gym or something, it's like, it's giving some things, what they call them, some nutrients, kind of, which will allow me to perform better, right? And by passing this additional kind of information, and as anyone can imagine, relationships are very important in this kind of field. It's like, giving extra steroids, let's say, to the algorithm to be able to identify, relationships in the data sets underneath. And obviously, hopefully, it will be more effective in detecting kind of suspicious transactions. Prior suspicious transactions with suspicious flags, we need to pass it. So what happened in the past? This transaction in the past, was it considered suspicious or not? That information. And the rule signal. So the rules themselves, the standard logic rules, are actually being fed as well. So we know as well what the rules are saying. So the algorithm will take into consideration what the rules say, right? So even if the rules sometimes are sort of, not detecting a particular transaction as suspicious, the machine learning will know that. So it's very important. That could pass an additional piece of information. This is now in terms of mentioned code. There are different algorithms, which could see, you could say there are different approaches. It's not like there is one machine learning algorithm, a number of them. And some of them perform better, some of them perform less, depending on the data, etc. So for example, one of them, what I'm showing you over there, it's called, even by the way it's drawn, but I've selected this one particular because it's one of the easiest to explain, let's say. It's like called decision trees or random forests. In this case, it was a random forest, but I picked a particular tree, let's say, but it's pretty much a tree structure. So in this case, if you have to follow, for example, the first model is basically modeling transactions which are coming from country MT, Malta, and currency euro, right? So as you see, the top box sort of is saying it's picking up transactions where the deposit was withdrawn within a particular time frame. Right? So the algorithm detected that when it came to sort of identifying suspicious transactions or not, right? The deposit withdrawal kind of, the time between a deposit and a withdrawal was one of the key features which helped the algorithm to identify whether it was a suspicious transaction or not. So in a way, it's helping you as well to identify which features or which elements of the transaction lead to kind of deciding whether a transaction is suspicious or not. What information you should look most or is most important to sort of to give weight. So then the second box is, for example, the monthly withdrawal frequency. How many withdrawals in a month were done? That was the second sort of feature where this algorithm, in this case for this particular data set, it found that variable provided a lot of information to identify whether the transaction is really suspicious or not. So really, it's like a tree is sort of a set of variables when you can actually follow the path. So for example, if I start from the top, would a deposit, for example, withdrawal frequency, was it greater than a certain threshold or less? If it's less, then you move in one part of the tree. If it's more, then you go to the other part of the tree. And you keep branching down in the tree, following the path. So asking a question, and if it's a yes, you go one side, if it's a no, go to the other. And once you arrive down at the bottom of the tree, right, you'll get your answer whether it's suspicious or not.
And the tree itself you have built with all the knowledge it needs, which are the rules
exactly.
said before.
So this is a decision tree. So it's taking you, in a way, it's a learned decision tree, but it is one of the algorithms which, let's say, it's one of the easiest to explain, let's say, right? Because a human can just look at it and you can easily understand how a computer is taking decisions. Because it's step by step, you have two outcomes, yes or no, you follow that path, ask the next question, then take the next. So it's pretty much very easily explained.
I am actually impressed. That's how I understood that.
Okay. But as I said, this is just one algorithm. There are a lot of algorithms.
Right.
But what I wish to mention is some challenges.
Yes, please.
Machine learning challenges, in particular because of this particular domain and the data set of this particular domain. Because a machine learning algorithm needs fine-tuning for each domain, meaning the data set of that particular domain. Now, excuse me, the first problem or challenge when designing a machine learning algorithm in this domain is what we call class imbalance. What is class imbalance? So class imbalance is a situation where when you have your data set, let's say I have 1 million transactions, right? Obviously the suspicious ones is a very small fraction of all the transactions, right? So basically when you feed that data, if you feed it raw as it is, in many cases the machine learning algorithm will not learn, because if I have just a fraction of the transactions which are suspicious, right, it will see only very few instances of those suspicious transactions. So when compared to the whole data set, it will be biased, let's say, to the non-suspicious ones, right? So somehow, and there are techniques, obviously I'm just mentioning the areas which need to be tackled at this point, but there are techniques which help you, let's say, give more importance to the suspicious transactions when you're feeding them the machine learning algorithm. Otherwise, they will remain undetected, right? It's like, it's very, in a way, you can imagine. Imagine I give you, you're preparing for an exam, and you're sort of, doing sort of, you're preparing, working a lot of examples before going for an exam. I give you a lot of examples, focus on one topic, and only one example of one other topic. So obviously, you'll be much more prepared for the first topic. It's exactly the same thing.
That's the way it works.
Yes.
I'm imagining that the algorithm is a rhino, and that the data sets are birds. And when the bird is very little, the rhino doesn't react and just leaves the
Pretty much.
The bigger is my point.
Pretty much. And in a way, really, I mean, although obviously, but the techniques, right, that are used are pretty much doing that. That they are, let's say, although it is that the suspicious are really underrepresented, they are trying to help the algorithm or pointing the algorithm towards those transactions, giving more weight. It's like putting a floodlight on those transactions, so sort of, they are given more weight. Something else is applying the correct measures. So in general, let's say for other scenarios, you would look at accuracy. And you say, okay, then, I have my algorithm, my machine learning algorithm, which is classifying, for example, between, I don't know, could be anything. But typically, you look at accuracy, okay, when I applied my algorithm, I got 80% accuracy, 90% accuracy. Let's say, for example, I have an algorithm which is detecting my handwriting, let's say. And that is typically, you just look at accuracy and say, okay, my algorithm is getting 99.9% accuracy, so it's really a good algorithm, right? In this case, accuracy is not a good measure, and I'll explain why. Let's say I have 100 transactions, and as we know, linked with class imbalance, I have only 2 out of 100, for example, suspicious transactions. So I tell you, if I get only those 2 wrong, I will still tell you that I have 98% accuracy.
Yes.
Right? So it's very important that when you're training the algorithm, you as well apply the correct measure. Because in this case, for example, you might think that, oh, I got 98% correct sort of accuracy, but I missed those 2, right? So it's very important in these instances that even the algorithm is provided the correct measure, because the algorithm itself learns by giving it the correct measure that it needs to take into consideration as well. So we need to give it the right measure, right? Something else. These are all complexities when applying machine learning in this domain, right? It's called this concept drift. And what is this concept drift? This concept drift is again another concept, because we are in an environment which is not static, in the sense that, for example, I'm sure that from a practical perspective, if we had to look at AML 5 years ago, right, I'm quite sure that even sort of humans who are doing this job would have told you that 5 years ago they were doing the process in a different way. Sure. And they were after particular transactions 5 years ago, right? I'm sure that today they would tell you, like, things changed, techniques changed, attacks changed, etc., etc. And they will. So what that means that for an algorithm, it needs to change as well, because the underlying data distribution has changed. So a model which I trained it on data coming in 5 years ago will not be effective today, because the underlying changed, right?
Yeah.
So in some cases, for example, if I have a model which is, for example, you see it today, let's say that it's detecting faces, for example, right? When I have a model detecting faces, if I went back 1,000,000 years ago, right, the humans were still humans, kind of thing, and practically looking the same with 2 eyes and nose and a mouth, kind of thing. So an algorithm trained 1,000,000 years ago, it will still detect a face, because the underlying data doesn't change. So there isn't this challenge, right? But with this environment, there is this challenge. So you need to make sure that you're handling this concept right when you're building machine learning algorithms. Another problem is data bias. Let's say I have an algorithm, and this is again another typical problem. And over the last year, I had people from a certain country, and I had 10 people from that. Let's make it simple. I had 10 people from that particular country, and it happened that 80% of those people from the specific country raised suspicious transactions. The algorithm automatically, if another person from that country comes in, right, will raise it as a suspicious transaction. But it could be unfair. So it's not fair that then a genuine guy comes from that country and raises a transaction, and because of those 10 others, automatically it raised my transaction as suspicious. So you have to be very careful when you're designing algorithms that you eliminate this bias,
Yes.
right, from your model. And the last point is this I'm calling interpretability, explainability, and causality. So it's very important that it's not like a black box. So there is a lot of machine learning algorithms are pretty much a black box. So you wouldn't know, okay, this is marked as suspicious, but why? It is not easy in many cases to translate. You have a black box and it's giving you output. So in many cases you need some form of layer which can, we call it explainability, which can transform a model from a black box into understanding even the causality. Why it resulted in this result? What caused this result? Right? Not just a black box. Because if it's a black box, it's sometimes, it's like you're removing transparency. And it's very important to have transparency. Why the model is giving me this result, right? Mm-hmm. So these are all challenges that a machine learning kind of person, who is designing algorithms in this field would need to think about, let's say. I think I can skip this, and this is, for example, final report that we generate out of the system. Okay. So out of the system, once you have all the generated kind of suspicious transactions about individual, I can generate a report. So it's like a SAR report kind of, right? Or it could be attached with the final SAR report, where it gives you all his activity, all his suspicious transactions, information that I scraped from the internet, being LinkedIn, Facebook's, public websites, etc., etc. The risk score on each transaction. Actually, so basically, we try to, as much as possible, compile a final report. And that report can then be passed either to sort of individuals so that they can take final decisions. The intention is to bring everything together. So his personal details, his activity, all the suspicious transactions that were raised, why they were raised, etc., etc. So we think that this would be, let's say, final outcome. Yeah, and based on this, we hope that an educated kind of decision can be taken on this particular transaction. Let's see.
Well, we're slightly over on time, so we'll gradually need to pause for today, but it's highly investigative work and beautiful architecture, like a Florentine cathedral. Truly, really enjoyed listening to you and learning as I'm sure our listeners did too. I think it's the first time that something as technical as machine learning and the beautifying impact which you mentioned, which is certainly there, was broken down into something more understandable, definitely. Thank you so much, Vince, for being with us, and we'll be with you next time.
Thank you.